Hi, my name is Gerard Andrews. I'm a product marketing director at Cadence, and I work in the Tensilica group, which is a product line of processors to address a number of applications. And today I will be talking about how to choose a DSP for IoT and wearable applications. If you've walked around the show floor so far, you've probably heard the word IoT between 50 and 100 times today. So please don't fall asleep in my presentation when I say IoT. Please stay awake. I promise it's going to be very compelling. So IoT means a lot of things to a lot of people. So I thought this diagram might help me address what I mean when I say IoT and where specifically Tensilica has a play. So of course there's a cloud which is going to handle all this data that is generated by a massive number of sensors that are impacting our lives, from our vehicles to our wearables to our home. In the Cadence vernacular, we call it the fog, the aggregators, which connect and aggregate from different devices and sensors and actually speaks to the cloud, to the actual things when we talk about IoT. Your white goods in your home, your thermostats. Maybe we have a Nest thermostat user here, your Google Glass, your wearables. These type of applications are the things, and this is where I'll talk about a processor that fits into things. So some of the key careabouts of these things for a hardware company are creating devices that can be very low cost, very low energy. As you move your processing capability closer to the sensor technology, you really like to have that to be low power. These things are often battery operated. There's a lot of innovation on unique form factors, different sensor technologies, and this concept of being always alert. I think we all have mobile phones today, which if you have a newer model mobile phone, you can issue a command word or a hot word and have your phone wake up and be ready to respond to you. That means we're going to be getting used to having microphones in our lives that are always listening. They're always alert, waiting for us to engage them and go to the next level of responsiveness in this device. And this always alert capability creates new processor requirements to be very, very low power if you're going to have something that's really always sitting on. At least when you look at the world of IoT and you're specifically talking about the things, the types of things that go on in these devices generally falls into three major categories, and most of the industry kind of agrees that these are the big buckets of processing functionality. So there's the sensing, there's the computing, and then you must communicate from that sensor node back to another device. So in the sensing thing, we have, like I mentioned, the voice trigger, which would be where you say in the case of Google, you say, "Okay, Google," and you wake that device up. That would be a voice trigger. There are a number of folks investigating applications like a face trigger that once the sensor realizes their face is actually looking at it, then the device will wake up in the case of a wearable watch applications. So a lot of different triggering which allow you to trigger the device, bring up some responsiveness without you ever having to touch the device. Some devices will wake up based on you actually making some type of gesture and goes, "Okay, I'm being moved in this pattern. It's time for me to wake up and see what the user wants to do with me." Computing, a bunch of the computing that's going to be going on in these IoT devices is really the voice pre-processing to clean up the voice signal before it sends it off to a voice recognition engine. Some devices might have simple command and control available on that device for you to say, "Play music, stop music, rewind music." That might be a local voice recognition task. But in many cases, there's a natural language processing capability sitting somewhere in the cloud on Google server where you can say, "Hey, what time does the movie start?" In these types of environments. And there's a lot of investment from folks in the industry on how do you handle the voice as you move more than 1 meter away, 2 meters away, 3 meters away? How do you handle the voice when the television is on and you're 5 meters away? So there's a lot of great compute capability in IoT devices around handling noise and being able to interact verbally. One of my favorite examples is, and this is a real IoT, someone wants to make a voice-controlled water faucet. So if you want to make a voice-controlled water faucet, it's very easy to say, turn water on. Okay, follow me, the water's on. Now when you say, turn water off, maybe that microphone can't hear you because the water is actually coming down and is making it very hard to hear your voice. So there's a lot of potential DSP processing to go, how do I cancel this rushing water noise out so I can still pick up that voice? And where is that speaker standing? So, you know, a lot of things of turning the thing on might be easy, but once you're in that environment, the thing that you turned on might have introduced new noise that you have to now and go cancel. For another example would be if you had your phone, you say, play music right now. And you say, play music. It was easy for it to hear you say, play music, but now the music's playing. And when you say, stop the music, how do you cancel the music that you just started? So your device introduced noise right into your stream that makes it more of a challenge. And this is where we think good DSP processing with good DSP capability with good IP from a number of our partners will really help. And then, of course, you must communicate it. And there are a number of standards that are emerging. Bluetooth Low Energy, 802.11 AH, where narrowband communications will be leveraged to communicate from these new set of IoT devices to bigger devices like your smartphone, your PC, your router, or different aggregators that'll ultimately talk to the cloud. When you talk to a person in IoT, some person may be really focused on the sensing part, or someone is really focused on the computation part, or someone is also really focused on the communications part. You're not quite clear, how do I choose a little processor, because it must be cheap, it must be low power, it must be low cost. How could I have a processor to do all three of those things? So I kind of discussed a little bit of this on the slide before, but just reiterating to make the point, no processor core is exactly uniquely qualified to do all three of these functions really well, the sensing, the computing, and the communicating. And as you look at what is fundamental in each one of these applications, the DSP workload of cleaning up the data from the sensor, of cleaning up the voice signal or running the voice recognition engine, or actually doing the MAC and physical layers of a narrowband communication standard really boil down to DSP problems. So the processors that are ideally suited to handle this type of workload need some DSP capability. And then as with most of these things, especially if you have a wearable today, you know the battery life is a huge concern. So you must be able to handle these three functionalities, and you must be able to do it in a low power footprint. So I want to introduce the product that we came up with at Cadence to address this market. It is called the Diffusion F1 DSP, and it really has three main attributes that make it uniquely suited for the IoT market. One of it is it's very leading low power for always on type of applications. And generally, the things that are staying on in today's devices are the voice trigger function and the sensor fusion function to give you some contextual awareness. These type of things are not getting turned off on the device. If your phone knows if you're moving, your phone can detect if it's in a purse. I've heard some cases where even the microphone is being used to give you more contextual awareness. There's a sound footprint of being on a train somewhere in Tokyo, and so some folks will have the microphone listen and go, "Oh, you must be on the Shinkansen." These are, once you start combining this with other sensor data, the device that you have can make some decisions about what you might want to do next, and you really need a low power DSP processor to handle this always on functionality. The next thing we have is a very high level of configurability. because the IoT market is so broad, spanning home appliances, refrigerators, white goods, to the smallest wearable devices that you might find in a device like this that has a little step counter and a Bluetooth radio. It go all the way down from here to, the Amazon Echo, which is quite a powerful IoT machine that's gaining a lot of notoriety in the market. So it's a big range of applications, and so the processor that you select should be highly configurable, where you include in the processor only the functionality you need for your application, nothing extra. And we offer that with the Diffusion DSP. And then you need a software ecosystem. You might need communication software. You might need communications Mac, or you might want to run the PHY of the communication standard on the DSP, or the voice pre-processing. So any processor that you propose for this application needs a wealth of software with it to be accepted in the market. So here is a block diagram of the Diffusion DSP. And one of the things about this DSP that makes it different from other DSPs is there is a base DSP architecture, and it's a two-way VLIW machine, and it's a 32 by 32 single MAC machine, and it's a dual MAC machine for 24 by 24 or 16 by 16. And then all these things here in the blue are ISA extensions, instruction set architecture extensions, that are added to the device, where you just select the click box when you are getting ready to build your device with the DSP, whether you need to include those functions in your specific instantiation or not. So there's a single precision floating point unit available, where a customer might say, I'm going to run a lot of sensor fusion processing. Most of the libraries are written in floating point, so I need a floating point library. So you might include this. 16-bit quad MAC. I'm going to be doing a lot of 16-bit processing on this machine, so instead of having a dual MAC, I would like a quad MAC architecture. You would include that. These three here, Viterbi, soft bit DMAP, and advanced bit manipulation. You say, I'm going to be running multiple narrowband IoT standards in my device, which means I would like a software-defined radio approach, and I would like to be able to run Bluetooth Low Energy and 802.11h on the same device. You would include these communications-driven ISA extensions in your platform if you're going to use it to do the communication. If you're going to use a different external radio solution and you weren't going to run the radio on your Fusion device, you don't include those instructions. So that's what I mean about a high level of configurability that allows the end customer to choose the exact instruction set for what part of the IoT problem his particular project is addressing. If you, like I said, we even have more things for AES 128 acceleration if you wanted to use this to do some of your cryptographic communications. And then we have one more option, the AVS, the audio, voice, and speech option, which can make the Fusion device compatible with the Hi-Fi DSP product line and its entire ecosystem of audio and voice software packages. So if your device, let's say, was going to play back MP3s or play AAC music files, you would include the AVS option, and you'll have a whole list of software IP available to run on that processor. Again, the idea is simple, though. You start with a common DSP core, and through clickbox options, you extend your instruction set architecture to the application in which you are targeting. There's another layer of configurability that is available in the Tensilica product line, and I'll fill this slide out and explain what some of those functions are. So if you look here, this is the block diagram I showed before, and these are things that you could do right from the configuration editor. You just check box and you say, all right, I need the floating point unit, I need the AES unit, I'd like the 16-bit quad MAC, and those things are included in your processor. Your company may have some special IP that is in your from your R&D groups, and in that case, you could you would examine this software, profile this software, and you could potentially find that I can even accelerate this algorithm even further by adding some specialized instructions. So in the world of Tensilica, you can pre-configure your DSP and take what we have here, and you can further extend it. We use the term extensibility, further extend it to meet your own processor needs based on your understanding of your system architecture. And you send this to our processor generator. It's a group of servers located in our headquarters in San Jose, California. And the output of that processor generator is your complete hardware design with pre-verified RTL, EDA test suite, as well as the associated set of software tools. So compiler, assembler, linker, IDE, compiler. And this software is unique to the processor that you just created. The processor that you configured, the processor that you augmented with your own special instructions. The processor generates, not only generates the hardware, it generates the associated software tools that go with it. So if you made a special instruction that used 17-bit floating point that no one else in the industry is doing because your algorithm is uniquely suited for 17-bit floating point, and you didn't want to do it in single precision, so you made up your own format, and you added an add, a subtract, and a multiply for that format, you know, at the end of when you got the output from the processor generator, your new compiler would understand your new machine. And that's part of the real value proposition of Tensilica and the Diffusion DSP. Now, we predefined a bunch of instruction set extensions that we think are relevant for the IoT market. But we know the market is changing fast. People are inventing all sorts of new technologies. New sensors are coming on the market. It's impossible to anticipate all the needs. That's where this part will have the end customers, the end licensees to be able to extend it further is a big part of the value proposition. Because we know a lot about the voice preprocessing part. We know a lot about the voice trigger part. We've optimized that very heavily, but there are new areas of innovation, and we give the tools to our licensees to be able to extend that and capture that. I had mentioned before that a big part of the value proposition is having low power. The next part is high level of configurability. And the third thing is to have some software and an ecosystem available to help your time to market. So from Cadence, we provide a lot of software for the Fusion processor. We have a DSP math library full of the fixed and floating point routines that you might expect to find on a DSP architecture. FIR filters, IR filters, FFTs, the trigonometric libraries that you might find. We also supply all the industry standard voice codecs, audio codecs, a DSP audio processing framework, as well as face trigger software. These are softwares that are directly available from Cadence. And then where the special sauce comes in is all of the software you might find in an IoT system that is available from our ecosystem. So we have a number of partners. These are all, this is a subset of our partners. These are the ones that we are we have the ability to publicly announce. But from the voice trigger side, of course, we have Sensory is one of our key partners. We have partners in the sensor fusion side of the world, as well as voice preprocessing. So a licensee can architect his core and then architect his software system with a lot of variety off-the-shelf ecosystem partners. And we think that's critical to get a product out in time to capture that market opportunity. If you have a great idea and it takes you too long to get to the market, this market is evolving so fast you may have missed that opportunity. I mentioned some of this before, but I think I'll go back on this slide just to show how you might use the configuration tool to map your core to a different application. So Maybe I'm making a activity wristband, and I'm going to need a voice activation feature for my wristband, and I'm going to use the DSP to do wireless communications on this wristband. So if you were doing those things, I would include the 16-bit quad Mac, and if I was doing you can see this whole row here. If I was doing the activity band watch phone, I would include all of these options here on the bottom. In an automotive application where I'm just doing voice input and audio playback, I would not include the AES, Advanced Bit Options for Turby, or the Soft Bit DMAP, because those are really associated with communications, and there's probably a modem somewhere else in the car. So that's the case where you wouldn't include that in your DSP. I just wanted to show an example of different applications that are a part of the big world of IoT and how you might configure your DSP for each one of those applications. Now, the good thing about it is if you have a multi-product product line, all of the software that you do for your RTOS, the infrastructure, your frameworks would work across multiple applications, even if you didn't include the exact same DSP core for your different applications. So you could make an activity band, and you could make one that also is more of a wrist, more of a smartwatch that has more capability, but your RTOS work, your framework, all of that would be reusable across multiple products, which is a real value for OEMs that have multiple products. Okay, so this is kind of wrapping it all up, and I think, again, you guys are probably very familiar with the IoT market, and we generally, all of us segment it the same way. Sensing, computing, and communications are the three big functions that go on any IoT processor platform, and when you choose an IoT processing platform for one of these applications, DSP is important, and DSP will increase in importance. At least that's our viewpoint. I can't emphasize the trend that we're seeing as voice input in the IoT device is becoming more and more important. I mean, it's quite obvious there is no keyboard and there's no mouse, so how do you interact with it? But I think some of the early popularity of some IoT devices like Amazon Echo and how compelling the user experience has been is even driving more fuel and more people to look at what is my voice input on my IoT device. I've heard one, it's not my own, but I asked a friend of mine why he has 4 of these devices in his home, and he says his family is so addicted to it because there's no learning curve to be able to talk to it. Well, you know, if you have an application on your phone and you click and you have a menu and you have to go down, and there is some learning curve. He goes, but for my family, there is no learning curve. Well, I just talk to it and it does what I says. And so I think that is a big part of what voice as a UI could mean. And I think it's going to be very important on the IoT market because we don't have a keyboard, we don't have a mouse. So how are you going to get that thing to do what you want it to do? So our proposition is you need a DSP, you need a flexible DSP, but one of the things you want to consider is your DSP good at handling voice? So that's, I want to thank you for stopping in.